Hello, Matt here from ChemistryStudent.com. In this video, we're going to look at calculating activation energy using the Arrhenius equation and Arrhenius plots. We're going to talk about how the Arrhenius equation can be rearranged to find activation energy for a reaction using experimental data and Arrhenius plots. And we're going to have a look at finding the Arrhenius constant for a reaction as well. Before we talk in detail about using the Arrhenius equation, it is essential you are comfortable with what the Arrhenius equation is and what it's used for. This has been covered in much more detail in a separate video. Check the links in the description below. As a quick refresh for this video, however, the rate of a reaction can be considered in terms of the total number of particles present, based on their concentration, and by the proportion of those particles that are colliding with the required activation energy and correct orientation each second. At a given temperature, this proportion of particles will always be the same, a constant, meaning we show it in rate equations as K, the rate constant. This rate constant can be calculated using a times e to the power minus Ea over RT, and this form of the expression is called the Arrhenius equation, where a is the Arrhenius constant and describes the proportion of collisions occurring between particles per second that have the correct orientation, and e to the power minus Ea over RT represents the fraction of reactant particles that have at least the required activation energy, where Ea is activation energy, R is the gas constant that links the energy of a gas particle to temperature, and T is temperature. To remove the E component from the expression, we can multiply the Arrhenius equation by ln, natural log, and get the form ln K equals ln A minus Ea over RT. Recap done? Let's go. As the Arrhenius equation is just that, an equation, it doesn't have to just be used to find a rate constant K for a reaction. The Arrhenius equation can also be rearranged and mashed up a bit to enable the activation energy and Arrhenius constant for a given reaction to be calculated using experimental data. To find activation energy, we can use what are called Arrhenius plots. Arrhenius plots are graphs made using experimental data that have ln K on the y-axis and 1 over T on the x-axis. K there being the rate constant and T being temperature. Data is obtained by carrying out a given reaction at different temperatures, T, and measuring the reaction rate and determining the rate constant K for the reaction at these temperatures. When the data is plotted, a straight line graph is produced. Now, a straight line graph always follows the standard function y equals mx plus c, where any y value on the line equals m, the gradient of the straight line, multiplied by an x-axis value, plus c, the intercept, where the line crosses the y-axis when x is 0. If we look at the natural log version of the Arrhenius equation, ln K equals ln A minus Ea over RT, we can see that this version can actually be rearranged to follow a y equals mx plus c form, as in ln K equals minus Ea over RT plus ln A. To help break apart the Arrhenius expression a bit more, minus Ea over RT is the same as minus Ea over R times 1 over T. It's just a bit easier to break this up and write it as minus Ea over R times 1 over T, as it keeps the Ea, activation energy, and temperature separated from each other. This now gives us ln K equals minus Ea over R times 1 over T plus ln A. If we compare this to the y equals mx plus c function, then the y part is ln K, the m part is minus Ea over R, the x part is 1 over T, and the c value is ln A. This may all seem a bit random. However, if we look at our Arrhenius plots, remember ln K on the y-axis and 1 over T on the x-axis, then the straight line graph will actually follow this form of the Arrhenius equation, where m, the gradient of the line, is minus Ea over R, and c, the intercept, is ln A. Now, to find the Arrhenius constant, or A, all we have to do is get the ln k value on the graph when the 1/t value is 0, as if ln k equals minus Ea over r times 1/t plus ln A, and 1/t is 0, then ln k equals minus Ea over r times 0 plus ln A. Or, in much more simple terms, ln k equals ln A at this point. To convert ln A to A, we just need to use e to the power ln A. Lovely and straightforward. Finding Ea, the activation energy, is a little bit trickier, however. We said the Ea over r part of the rearranged Arrhenius equation is the same as the m part of y equals mx plus c, and the m is the gradient or slope of the straight line. Gradients are calculated by taking the change in y value of a straight line and dividing it by the change in x value. You may have heard this said as rise over run. This means if we calculate the gradient of the line in an Arrhenius plot, it will be the same value as minus Ea over r. Well, r is a constant, 8.31 joules per Kelvin per mole, meaning the gradient of the line times 8.31 equals minus the activation energy of the reaction. Activation energy then equals minus 1 times the gradient times 8.31. The only small thing to note here is that activation energy is given as kilojoules per mole in chemistry, and as the gas constant has joules in its unit, we need to divide the value for activation energy obtained from the Arrhenius plot by 1000 to get it into kilojoules per mole. So, to summarise, Arrhenius plots can be used to find the activation energy for a reaction and the Arrhenius constant. Ln k is placed on the y-axis and 1/t is placed on the x-axis, with k being the rate constant and T being temperature. When the data for a given reaction is plotted, a straight line graph is formed. By taking natural logs of the Arrhenius equation, the form ln k equals ln A minus Ea over RT can be rearranged and twisted into a form that matches y equals mx plus c, which is the equation for a straight line graph, where ln k is y, minus Ea over r is m, 1/t is x, and ln A is c. This gives ln k equals minus Ea over r times 1/t plus ln A. The m in a y equals mx plus c function is the gradient of the straight line given by the function, and the c is the intercept, where the line passes the y-axis when x equals 0. For the rearranged Arrhenius equation, the gradient of the straight line, m, is minus Ea over r, meaning change in ln k, or 1/time, divided by change in 1/t equals minus Ea over r. R is a constant value, 8.31, meaning Ea can be found. Ea equals minus 1 times the gradient times 8.31. We need to divide this value obtained by 1000 to get the activation energy in kilojoules per mole, as the gas constant has units based on joules per mole. The intercept of the straight line on the y-axis is the same as ln A, meaning at the intercept ln k equals ln A, and by using e to the power ln A equals A, we can use the graph to find A. I hope you found this video useful. Please check out other relevant videos in the links given in the description below, and visit chemistrystudent.com for free notes and revision materials.